Yeah. I started my living. I already know what kind of so it doesn't take that long. That should load it. So, it's not too bad. I think the longest one is just that right up. That's gonna be all right. So that's probably what I'll do. And then what I'm gonna do on these computers, the student relationships. Yeah, that's good. I think I'm gonna do 1, 2, 4. I haven't really taken a solid look at 3 yet. The first one is just going to be about the way. That's the one where we do. Yeah, that's right. The first one, the first problem is that you just set up your S4, S3, S2, S1. Yeah, that's what I was thinking. And then when you get your determinant, you have to say like this is when they determine it. It's only going to be. All the determinants should be constants beside that key. So that key is going to be like K when you do. Yeah, yeah. And then you have to say that when K is less than this, then it's stable. If it's more than this, because you can look at it already just like a problem and say just from looking at it, that K has to be greater than 1, right? Because it can't be 0 or negative, right? In the characteristic equation, it can't be, because all of those A's have to exist and be positive in order for it to be stable. So you can already say that it has to be greater than 1. Yeah, and then so you get more specific when you set up that array, right? Yeah, you'll have K minus, like say it's K minus 1, and like K has to be equal. Yeah. Or the other way around. It's 1 minus K. Okay, so that makes sense. Dr. Tran, you did end up extending the assignment? I did. You asked too soon. That was the problem. I came in here on a Friday. I was like, I gotta get it done. Yeah, it was. Yeah, I didn't realize there was a lot of people that were struggling with it. So yeah, I didn't know. That's why I asked you. I'm like, hey, is anybody else asked? Just me. Yeah, I part of me was like, because I already told you no, and so I didn't want to change my mind on that. But there was a lot of people that were messaging me on Friday, and so okay, that's what I was trying to inquire about, and then you made me feel like I was the only one. And I was like, all right, I guess I'm the stupid one. I got to get this done. No. I mean, you're the only one at the time, but it doesn't make you stupid, right? No, it didn't end up working out because I had like we went to Universal Studios on Saturday, so okay. I helped not having it because I was going to do that in the morning if you gave me the time to do it. I see. There was another class actually. You gave me a hard time about like the whole after hours pass and everything. Yeah. Past 5 o'clock, and I come in here and there's a class, and I'm like, I see. I mean, I guess I can use it on Saturdays and Sundays as well. So. Okay, that's good. You could. I signed the paper this morning. Did Dr. No and Dr. O sign it? They're gonna call me down there to sign something. Okay. Give me the pass, so okay, great. Okay. I mean, you've been kind of using it, but now it's official. Yeah. You can actually stay here. I'm aware it's bad. Yeah. But I didn't tell him that you've been in here normally. All right, it's 5:30, so let's go ahead and get started. Good evening, everyone. How's everyone doing today? Good. Hope we're having a good weekend. Huh? What's that again? Oh yeah, sure. Yeah. I was yeah. So I feel bad because other people ask, and usually I kind of wait for that to kind of reach critical mass before I send something like that. So it was a little bit of an awkward situation because I said no to some people at first, and then a lot of people asked them. So, but hopefully that extra day was helpful for a lot of you. Okay, and so today we're going to be going over shell and beam elements. Okay, and so these are special element types that we're going to use in our activity on Wednesday. Okay, and so this is kind of the precursor lecture that kind of explains a little bit what we're going to do. Okay, but it's all under the general umbrella of meshing, right? And so we're still going to be talking about meshing, but today we're going to talk about a special type of element. Okay. Because up until this point, or for all of last week, I'd say we covered I would say kind of the general elements that are available within ANSYS and a lot of finite element software. But there's more element types out there that fit certain situations better than others, and so that's what we're going to go over today. And then on Wednesday, we'll actually put that into practice into an actual activity. Okay. Okay. And so I think that's it for the announcements. Okay. So I haven't posted the activity yet because there's a couple adjustments that I want to make. And so it's an activity I've run in previous years too, but I want to change a couple of things before I post it. But you'll have the activity PDF and the CAD file before Wednesday for sure. Okay. All right. Are there any questions I can answer before we get started today? Okay. All right. So let's go ahead and get started. And so the topic for today is going to be shell and beam elements. All right. Okay, so far, we've covered a bunch of different element types, but they all kind of fit under the same category, as what I would call it. And so far, we've covered what I like to call the solid elements. Okay? And so, from this point forward, I'm going to assume that we're strictly in 3D. Okay. Actually, let me write that down first. And so when I say that, when I say the standard elements or the solid elements, I'm specifically referring to tetrahedrons and hexahedrons. And the reason we call them solid elements is because the elements themselves form a solid volume, a solid three-dimensional object. Okay, and so all of these elements have height, width, and depth because they're 3D. Okay. Okay. And so we've talked about these as kind of your only options for meshing a three-dimensional object, right? And so let me talk a bit more about what situations where these elements actually work really well without any issues. Okay. Okay. And so if you look at a hexahedron, if you look at a tetrahedron, right, and you draw them as in kind of their standard equilateral form, you'll notice that they have approximately the same shape factor in each dimension. Okay. Right. And so I think the easiest way to imagine this is for a hexahedron, right? And so if you imagine all the sides of that box having the same length, right? And so you literally just have a cube, then you can say that it has the same dimensions in every direction. Okay. And so because of that, these element types, these solid elements work really well to mesh objects that look the same as that, right? And so if your solid, if your solid object has roughly the same, height, roughly the same width, and roughly the same depth, right? So all three dimensions, they don't have to be exactly the same, but if they're all on the same order of magnitude, then your solid elements are going to work really well for these. Okay? Right. And so if you look at, an example that I have here on this desk is like this mouse, right? And so if you look at this mouse, if you look at the length of the mouse in this direction, the width of the mouse in this direction, and then the height of the mouse in this direction, right? They're not exactly the same, but they're all roughly the same, right? And so, I would say that this, if you were to do a finite element analysis on this mouse, you could do it just fine with probably most likely tetrahedrons, because it's so curved. Hexahedrons might struggle a little bit with this one, right? But there's a lot of engineering geometries that actually don't fit this bill, right? And so what I like to call them is these are geometries that are either thin or slender, okay? And so these are geometries where I characterize, at least one of the dimensions is significantly smaller than the other ones. And so one example here that I have just right in front of me is like my phone, right? And so if you look at my phone, right, it's kind of the width of this phone and the height of this phone are kind of roughly the same, right? And so they're kind of same order of magnitude. But if you look at the thickness of this phone, it's a lot thinner than it is, tall or wide, right? And so this is what I would consider like a thin geometry, because it's, you have one dimension of the phone, which is much, much less than the other ones, right? And so for an example for a slender geometry would be like this pen, right? And so for this pen, you have one dimension that's fairly long, which is the length of the pen. But if you look at kind of the cross section of the pen, both dimensions in this direction are kind of much smaller than the other one, right? And so that's something I would consider a slender geometry, okay? And so for these types of geometries, if you try to match them with solid elements, they can struggle a little bit, right? And so, what's actually more efficient to use in this case are, more specialized element types, for these situations, right? And those element types are called shells and beams. Okay? And so in today's lecture, we'll talk about what shell and beam elements are, what makes them different from the solid elements in terms of their computational cost and in terms of how they compute quantities. And then we'll talk about, how do we actually use these, in a finite element analysis. Okay. All right. Any questions on this so far? Okay. All right. And so, how do we, how should we think about this, right? So let's start with thin geometries, right? Okay. And so thin geometries, we have, I consider these to have kind of one dimension which is smaller than the other ones, and so that's what makes them really thin, right? Okay. And so when that one dimension is much smaller, we can basically ignore it from our analysis, right? And so we can basically say that, the thickness is so small, we'll just ignore it. And so instead of considering this as a three-dimensional object, let's instead consider it as a two-dimensional one. And if you think back to, what we talked about last week when we compared 2D elements compared to 3D, right? And we saw on a per element basis, 2D elements were a lot cheaper in that they had less nodes, okay? And less shape functions and less degrees of freedom. And so, if we can replace some of our 3D elements with 2D ones, and we do this a little bit intelligently, we can actually save a lot of cost, right? And so for slender objects, these are kind of the opposite, where they have kind of one dimension that's significantly bigger than the other two. Okay. Right. And so basically those other two dimensions may as well not exist for these objects, right? And so we can save a lot of cost if we consider these slender objects as a 1D object. Okay. Right. And so basically, we're going to take if I can draw kind of an image for you, okay? And so we have kind of a very thin plate like this, okay? Right. What we want to replace this with is just a literal piece of paper or a literal sheet, right? Okay. And if we have a three-dimensional beam, right? So let's say that we have a beam like this, we're literally just going to replace it with a line, okay? Okay, and so this would be the 3D versions of these objects, okay? And then we're going to reduce this down to 2D for the thin geometry, and then for the slender one, we're going to reduce it to a 1D, okay? And so these special element types, an element type that can basically take a 3D object and replace it with a 2D one, these are called shells, okay? Whereas a 1D representation of a slender 3D object, we call these beams. Okay? Hence the name of the lecture today, shells and beams. Okay. Right. And so we'll talk about each one individually, but to kind of give a kind of a general definition for them, shell and beam elements are a lower dimensional representation of a three-dimensional object. Representation, I should say, of special 3D objects. Okay. And they're unique in that they have a different mathematical formulation. Okay, we're not going to go into what that formulation is, but we'll talk about kind of the effects of that formulation. Okay. And this formulation kind of gives us two main benefits, right? And it almost seems too good to be true, because what this different formulation gives us is that it'll give us a result that's cheaper, right? And so it's not going to take as much computational cost to use these small elements. Okay. Right, and so you'll have less nodes and less elements overall, okay, when you switch to shells and beams, okay, for a specific case. And it actually gives you a more accurate result. Because remember, usually we don't get this. And so usually if we want to get something cheaper, right, we want to have a cheaper finite element simulation, we're going to have to sacrifice accuracy. Whereas if we want to get a more accurate finite element result, it's often going to cost us more computational power to do that, right? And so the use of these shell and beam elements actually gives us both at the same time, which is a very unique thing. And so where the difficulty lies in is first of all, recognizing when you can use these elements. And a lot of times you have to kind of fix your geometry a little bit, or sometimes even design your geometry from scratch with these elements in mind, right? And so I would say they're not the easiest to use, compared to the other elements, because they take a little bit more special setup. But when you are able to use them in your finite element simulation, it can make a huge difference in terms of what you're computing. Yeah. All right. Any questions on this? Yeah.
What do you mean by they're more difficult to implement into your?
We'll get into that a bit later. So with shells and beams, it's more, because right now when you mesh something, like you can basically import your CAD geometry into ANSYS and you can just hit mesh, right? For shells and beams, you actually have to modify the geometry a little bit. And so if you have a thin piece of geometry, you have to explicitly say that I want a shell here. And you might have to actually move some things around the geometry to actually make sure that things still connect. Yeah. So we'll talk about some of the complexities today, and then on Wednesday when we do the activity, you'll kind of see that it can be kind of difficult to do. Yeah. So on Wednesday, I'm giving you an activity with on purpose with the geometry that's not, I would say, not very clean. And so you'll see that once you start adding shells and beams, you're gonna have to do a lot of cleanup on the geometry to make sure that it's actually still usable in the finite elements. Okay. All right. And so, what makes them so special? And so what gives us this benefit where it can be both cheaper and more accurate, right? And so compared to solid elements, okay, remember, when we use solid elements, we're mostly computing one primary thing in our finite elements, right? And that's the deformation. Okay. And so, so far for all the activities, when we do a static structural simulation, we're computing XYZ deformation at all the nodes. And then from the deformation, they compute things like the strain and the stress and all that stuff, right? And so that's what you're computing for solid elements. Okay? For shells and beams, you're of course going to be computing the deformation. But in addition to deformation, at each of the nodes, you're also going to be computing 3 additional quantities. Okay? And those three extra things are going to be the three components of rotation, right? And so normally if you have kind of a solid element like this, right? Actually, let me just do, I'll do 3D. Okay. And so for any given node right here, you're going to compute, on the deformation in the X direction, deformation in the Y direction, and deformation in Z, okay? And so that's normally what you're going to compute for this, okay? But for, let's say, a beam element, okay? Okay. Here you're going to compute, how far this node is going to deform from its previous state, okay? So you're going to do dx, dy, and dz, okay? But you're also going to compute the rotations, okay? So Rx, which is rotation about the x-axis, Ry, which is rotation about the y-axis, and then Rz, which is rotation about the z-axis, okay? Right. Right. I think probably the symbol that's more common for rotations that you've probably seen this in beam theory is to use theta. Right? Where basically, this rotation, it's a fancy word, but basically it's a determination of what the slope of the solution is or what the slope of the deformation looks like at that location, right? And so we're not only going to compute, let's say that the beam, deflects to above here, okay? But we're also going to compute, what's the actual slope of the line here at those locations, okay? And that's the rotations. Okay? Right? And what these rotations do, right? And so, per node, we're going to be computing twice as many things relative to a solid element. But what this does is that, with these rotations, we're able to compute things like strains and stresses, with a greater degree of accuracy than, compared to before. Okay? And I'll expand on that statement on the next page, because it's kind of an important point for why shells and beams are better in certain situations than solid elements. Okay. All right. Okay. Any questions on any of this? Okay. All right. And so the big reason why we say that these rotations give us a big advantage is that when you have the solid elements, which it computes just the deformations, x dx dy dz, the way that it computes stresses is that it first has to compute derivatives, right? And so that's one thing that we've been talking about last couple of weeks, is that strain is a derivative based quantity, and then by extension stress is also a derivative based quantity. Okay. Okay. And we haven't really talked about this yet, but the way that finite elements computes derivatives is that it utilizes a method known as the finite difference calculations. Okay. Okay. And so, finite difference is a big method that we can spend a lot of time talking about. But I just kind of want to make kind of one important point here, right? And so let's say that we have a particular element like this, okay? Okay, so let's say it's a 2D element, and let's say that we want to compute the derivative of the solution in terms of x, right? And so the way it does this is that it literally takes, the difference between two solution values at two different locations in the mesh, and then it divides by the distance between them, right? And so let's say that, let's say that the distance between these 2 points is Lx, okay? Okay. And so let's say that, we have the solution here at node 1 as U1, and the solution here at point 3 is U3, okay? And so the finite difference approximation of this derivative is literally just going to be U3, okay, the solution at node 3, minus U1, which is the solution at node 1, divided by the distance in between, okay, divided by Lx. Okay. Right. And so for cases where, you have a geometry that's not thin or slender, this is perfectly fine. And so if you have, a decently thick geometry where you have, lots of different elements in there, through every single dimension, you're going to be just fine doing this. Okay. But what can happen sometimes when you have a thin or slender geometry is you might have situations where you only have one, maybe two elements through the thickness of your geometry. Okay. And so what I mean by that is that if you look at your geometry and you look at your mesh and you go from one boundary surface to the other, you only cross, one or two elements. Okay. And so I'll draw a picture of this on the next page just to make it a bit more clear. But in these situations, you want to be careful about when you compute derivative-based quantities, because they can be a little bit unreliable because all of the nodes that you're using in this calculation, they're on the boundary, right? And so what happens is that, because these nodes are on the boundary, and in some cases, both nodes are on the boundary, you kind of already pre-prescribe what your derivative is based on the boundary conditions that you apply. Even if you don't apply any boundary condition on those spaces, the fact that they are on the boundaries means you're also subject to certain edge effects as well. Okay. But we'll talk about that more on the next page where we draw the picture. Okay. Any questions on this? Okay, so let's draw a picture just to show what can happen if you have a thin. I'll do a thin geometry just to make it a bit more clear. All right, so let's say that we have a very thin plate. Okay. Okay. Right, and so maybe this is part of your your finite element geometry. Okay. And then let's put a mesh on this, right? And so let's say that we mesh it in a way that looks like this. Okay. All right. And of course, these element edges go in this direction too. Okay. Right, in this situation right here, if we look from kind of the top of this geometry to the bottom, okay. kind of senior moment, bottom with 3 T's. Okay. And so if we go from the top of this geometry to the bottom, and so let's say that, we take this path, we'll just look at the very front, right, from here down this direction, okay? We only cross through one element, right? And so this is a situation where I'm saying that, we only have one element through the thickness of this geometry, okay? Okay. Imagine if we were to take a derivative in this case, okay? And so if we want to take a derivative in that direction from going from top to bottom, the nodes that we would use for that is this node right here and this node right here, right? And so both these purple nodes right there. Okay. And so the issue with computing a derivative with nodes like this is that both of those nodes are on the exterior of our geometry. Okay. Okay. And so that's usually not a good idea because, if you have nodes that are on the geometry, first of all, if you're applying a boundary condition there, like some kind of force or some kind of, fixed constraint, that's going to, kind of mess up the computation of the derivative there, okay? Especially if you apply a boundary condition on both. But also you can have, what I like to call edge effects, which is, when you're on the edges of your geometry, that creates some, sometimes undesirable effects on your solution, okay? And so you want to avoid situations like this when you're taking derivatives from nodes that are both on the boundaries. Okay. All right. And so what's one way that we can get around this is that if we instead replace this thin geometry here with just a simple 2D one. Okay. And so let's say that we replace this instead with a sheet, a 2D sheet like that. Okay. And then let's say we want to do the same exercise where we want to compute the, we want to compute, say the stress right here. Okay. And so instead of, if we want to do this on this situation here, instead of relying on a solution derivative, what we can do instead is we can use the extra degrees of freedom that we're computing, right? And so, we can utilize the nodal rotations here to compute the stress more accurately. Okay? And what this does is that this helps us avoid taking derivatives at that location. Okay. Right. And so the stress that's computed based on these rotations instead of derivatives. First of all, it saves you from computing derivatives, which is, in itself a little bit of an expensive process. Not that expensive, but it's something. And because these rotations are being directly computed from the finite element result, you're going to end up with a more accurate solution, overall because of it. Okay. All right. And so that's kind of that's the justification for why, when you can use shell and beam elements, you end up with a higher quality, cheaper solution overall. Okay. All right, any questions on this? And also backwards. Question from the chat. All right, so would it be possible to compute the nodal rotations for a solid element? So I'd assume yes, just needlessly expensive. Yeah, no, yeah, you're exactly right. And so it is technically possible to compute the rotations in a solid element. It just adds, a ton more cost. Yeah. You know, and it's not just computing three extra variables for each element. It actually modifies the equations quite a bit. And so, you know, it would have to be a whole new implementation for, you know, to compute those things. Yeah. Mm-hmm. Good question. All right, any other questions on this? Okay. All right, so let's you know, that's kind of the justification for why, you know, shell and beam elements are useful. So now let's talk about, you know, first when you can use these and how to actually implement these in practice. Okay. All right. And so, you know, throughout today, you know, I've just been mentioning that you should use shell and beam elements when your geometry is thin or slender with air quotes included. Okay. But what does that actually mean, right? And so, you know, is there, you know, I think that the fair question to ask is, you know, is there a threshold for when something is thin enough or slender enough that you want to use shells and beams? Okay. Because it would be really nice, you know, if we can say that, you know, this has certain geometric dimensions. And so, you know, for sure we should use we should use shells and beams for this. All right. So unfortunately, you know, there is no magic number. Okay. Because a lot of it is also, you know, application specific too. Okay. Because you know, there actually are some cases where you might have a thin or slender geometry. But if you don't expect there to be a large amount of stresses in there, or you don't expect there to be a lot of bending that's occurring, then it's usually safe to leave it as a solid element and to not have to go through the trouble of creating shells and beams, because it's and you'll see on Wednesday that, you know, creating shells and beams, it's a little bit of an ordeal, and it can be a little bit messy depending on, you know, what the geometry looks like. So, you know, it is application specific, and so there is no magic number. Okay. And if you ask different people, you know, they're going to have different opinions on this too. So it's also one of those things. But I will give you my own personal opinion and kind of my own personal rule of thumb to use. And I think it's, you know, and of course, in my opinion, I think it's reasonable, but, you know, but also other people might disagree with me. So kind of take this with a grain of salt. And so my threshold for using shells and beams is I like to use a 10% rule. Okay. And so what I mean by that is if there's a dimension that's less than 10% of the other dimensions, then I consider that to be thin or slender. Okay. Okay. And so as an example, you know, if you have a thin plate, and let's say that this is the height of the plate, and this is the length, and this is the width, okay? Right. And so you can see from this image here that the height of the plate is that's the smallest dimension that we have, right? And so my criteria is that if the height is less than or equal to 10% or 0.1 times the length, and h is less than or equal to 0.1 times the width, Okay. Okay. Then this is the criteria that I use to say that, okay, this geometry is thin enough that I can replace this with a shell. Okay. Right. And so this is my own personal, threshold, and it's served me well in the applications that I've used it. But I also know people that would disagree with me, and so just kind of keep that in mind. Okay. Any questions on this? Okay. All right, and so now let's talk about how do we actually incorporate these in practice. And so this is a little bit of a preview of what we're going to do on Wednesday, but I did want to talk about it in this lecture format before we're actually clicking stuff in ANSYS, just so that you know what's going on. All right, so let's start with shell elements. Okay. All right. And so the definition of a shell is basically a surface that has a very small thickness. Okay. So it's a 2D surface. Okay. So 2D surface has a small thickness. Okay. And so it's used to represent geometries that are very thin. Okay. But what it does is that instead of representing that thickness geometrically, and so instead of having an actual three-dimensional object, it instead flattens it into a 2D object, right, into a piece of paper basically, and then it stores the thickness as basically as like a material parameter, a material property. Okay. And so whenever you have a shell element, you actually have to explicitly put in a number that represents the thickness of that geometry. Okay. And so we've actually already used a shell element in our last activity, right? And so if you remember the application surface for the wind, okay, it was that piece of tape that was kind of running up and down the post and the sign, right? Remember before we could actually use that, we had to assign a thickness of that application surface, right? And so that application surface was actually modeled as a shell element, right? And so it was a 2D piece of tape that was running up and down the length of our signpost, okay? But before we could actually use it, we had to say that its thickness was 1 e to the -3 inches, okay? And so we've already used a shell element already in an activity, but now we're actually going to learn how to actually create them and really use them in practice, okay? All right. And so how do you create shells? Right? And so there are four methods that are available to you. Okay? And I would say only really one of these is probably the most practical, but the other two can be nice if you kind of plan ahead. Okay. All right. And so the first method is to create a 2D sketch and then basically assign it as a shell element. Okay. And so that's very similar to what we did in the first activity. Right? It's, remember when we did our plate with the hole, we created a 2D sketch, and then we had ANSYS say that, you know, this is going to be a 2D object. Right? And actually for that one too, we assigned the thickness, you know, as a parameter as well. And so we've actually, you know, we've actually seen shells a couple times. You know, we just didn't realize it at the time. Okay. All right. So the second method is to create an open sketch. And what I mean by open sketch is that it's basically a curve that doesn't end on itself, and so it's open in the sense that it's just a line. Okay. Okay. All right, and so we're basically starting with just a line, and then what we're going to do from that line is we're going to extrude that into a shell surface. Okay. Actually, let me draw what that one looks like, you know, before I move on to the ones. And so, you know, in order to use that that third method or that second method, okay, you're going to start with an open sketch. And so here's an example of an open sketch. Right? And so let's say that we draw a line just like that, okay? And then to turn this into a shell, you know, we're basically going to take this line and then extrude it into the page. Right? And so, you know, we're going to start with a sketch like this, okay? And then we're just going to extrude it into the page, okay? And so we end up with kind of a very thin sheet in the shape of whatever that we drew out, okay? Okay. Any questions on this so far?
What do you mean by sketch does not end on itself?
Yeah, and so this line that we have right here is an open sketch. And so if this were a closed sketch, you know, I would connect this end down to this one right here. And so the fact that it's open means that, you know, we just have a line where we have two kind of open ends on the.
Okay.
Yeah. Mm-hmm. Mm-hmm.
Okay.
And so these two methods here are nice if you're planning ahead, and if you're creating a CAD model specifically for finite elements, you know, you can use these first two methods, because basically, you know, you can already plan from the beginning that, you know, I have this thin part of this geometry, and so let me go ahead and just draw it from scratch as a thin shell, and then we can just import that into our ANSYS mechanical. Okay? And so if you can plan ahead and you have control over the CAD geometry, you know, this is a great way. These are two great methods to do that. Okay, but a lot of times you're not gifted with that opportunity, and so a lot of times you're often given a CAD model that someone else created for a different purpose, you know, and you want to run finite elements. And so in those situations, you can still use and create shells. It's just that you have to go about it in a different way. And so option 3. And this is the one that we're going to use on Wednesday. You know, I'd say this is probably one of the more common ones. And so this is to use a mid-surface, what's called a mid-surface operation. Right. And so what the mid-surface tool does is that it basically takes two adjacent planes, okay, and then it creates just a thin plane right in the middle. And ideally, you know, these two parallel faces should be pretty close to each other, right? And so that's what forms a thin body, okay? And so by creating a surface in the middle of them, you know, that kind of replaces it. All right, so let me go ahead and draw you an example here. And so let's say that we have a geometry that looks like this. Okay. Okay. And so what the mid-surface operation is going to do is that it says, okay, I have this plane right here in blue. Okay. That's really close to this other plane that's parallel to it, okay, on the other side, which I can't highlight without making this confusing. Okay. And so what it's going to do is that, okay, the two sides of this box right here, they're very close to each other and they're parallel. And so let me go ahead and create just a plane that's in the middle. Okay. Right. And so it's going to draw a shell that goes right in between them. Okay. And then it replaces that that plane with that shell. Right, and so that's why it's called a mid-surface, because it literally creates a surface in the middle of the two parallel faces. Okay. Right, and so that's the one we're going to use on Wednesday. And so from the geometry that I'm going to give you, you're going to use several mid-surface operations to compare to create thin shells. Okay. All right, and so this last one here is I would say this is something more niche to ANSYS, and so I've seen this done in ANSYS, but although I haven't really seen this in other softwares. Okay. But in ANSYS they have a feature called a thin surface tool. Okay. Okay. And what this will do is that this will extract a thin shell of an otherwise solid object. Okay. Right. And so let's say that we have a pure solid cube. And so this cube here is a solid piece of material. Okay. And so it's not hollow at all. Right. And so what this tool will do is that it'll basically take the solid object and then extract just the exterior shell around it. And so you can almost think of it as it makes your object hollow. Okay. So this is really hard to draw, but the way that it works is that it'll look kind of like the same thing as your object from before, but you're going to have one open face, right? And so to use this tool, you basically have to specify which surface on here has to be open. Okay. Okay. Right, and then all the other faces of this geometry, right? So all the other faces of the cube, they now turn into shells, which are incredibly thin. Okay. And so you can almost think of this as like, taking your object and just hollowing it out and then making a hole on one part of your surface. Right?
You have to define that thickness.
Yes, yeah. And so for this one, you have to define the thickness and you have to input the number.
So it's like similar to the shell feature in like SolidWorks where you shell it and you
yes.
do the thickness.
Yes. Yeah, it's exactly like that. I think if you use the mid-surface, it'll automatically determine the thickness because it already measures, how far the two parallel faces are.
Okay.
But for the other features, then you have to input the thickness yourself. Yeah. Mm-hmm. Yeah. So for number 4, I can't say I personally use this for anything other than just, just as tutorials. I mostly use, number 3 here. But, that one does exist for, for some purposes. Okay. All right. So, but no matter what, no matter what method that you use, you're going to end up with basically a 2D surface, that's representing a 3-dimensional object. Okay. All right. Any questions on this? Okay. All right. So now let's talk about beam elements. All right. And so a beam element is a one-dimensional element. And this is meant to represent slender geometrical features. Okay. Right. And so it's unique from the shell, whereas in the shell, we're basically eliminating one dimension from this from the object. When we're creating beam elements, we're essentially eliminating two dimensions. Okay. And so what this means is that, for shells, remember that we had to specify a thickness for our shells, right? And so for beam elements, we have to go a little bit deeper than that, right? And so, instead of specifying a thickness, what we're going to do instead is we're going to specify a cross-sectional shape. Okay. Because if you think of a beam, there's lots of different cross sections that are available for a beam. So you can have an I-beam, you can have a cylindrical rod, you can have an L-beam, right? And so, there's lots of different ways you can have beams. And, when you're eliminating those 2 dimensions, within the cross section, you have to basically, mathematically describe, what that cross section looks like. Okay. Right. And so we'll go over that on the next page and how you actually do that. Okay. But let's talk about, the cost for beam elements. Okay. And so because these are just 1D elements, these are extremely cost effective. Okay. Okay. And so if you want to talk about the number of elements in a 1D element, okay. Okay. And so the most basic 1D element only has 2 nodes per element, right? And so that's extremely cheap, right? And so even the quadratic one, right? When you go from a linear 1D element to a quadratic one, you only have to add 1 additional node. And so, I would say, the quadratic version of a beam element is probably the cheapest element that you can get that still gives you, good results. And so, these are really, really good. Okay. And so there's two main methods in order to create beam elements, and for FEM. And so the first is to create a 1D sketch and to assign it as a beam. And so that's very, very analogous to, the first two methods that we talked about for shells. Okay. And so method one here works really well if you have control over the CAD, and you can kind of plan ahead of time that you want certain parts of the geometry to be beams. Okay. But that doesn't happen all the time, and so a lot of times you're given a CAD model. Okay. And so in those situations, you're going to do method two, and this is the method that we're going to use on Wednesday, which is called beam extraction. Okay. And so what you're basically going to do is you're going to extract. You're going to extract slender parts of the geometry as beams. Okay. And that's mostly just a point and click process where we're going to turn on the extraction tool basically within ANSYS Space Claim. And then we're going to click on the geometries that we want to be beams and then just poof like that. And then they're going to turn into beams. Okay. And so it's a little bit of an easier process to than creating shells. But what you'll see is that kind of the difficulty in using this is kind of the cleanup afterwards. And so making the beams itself are easy, but making it work with the rest of your model can be difficult. Okay. Any questions on this? Okay. So let's talk about the cross sections again. Okay. And so it's really important for beams to know what their cross-sectional size and shape look like. Okay. Okay. All right, and so some examples of beam cross sections that you can have is that you can have a rectangular beam. Another popular one is an I-beam. Okay. And here we have an L-beam. Right, and because these are beams, you can imagine that they're extending further into the length of the page. Okay, and so they're all going to be extending this way, right? Okay. But whether you have a rectangular beam, whether you have an I-beam or L-beam, the shape of the cross section is gonna affect your results. Okay. Because each of these cross sections, they have a different moment of inertia. Okay. And so in order to solve the beam equations and to actually compute the rotations that we talked about, it needs to know what that moment of inertia is, and it gets that information from the cross section. Okay. All right. And so one quick tip, if you're and this is specific just to method one. Okay. And so in method one, where you're kind of drawing a line in your sketching tool and you're assigning it to be a beam from there. Okay. It can be useful to actually render the cross section within the CAD. Okay. Because what you're going to do on method 1 is you're going to basically draw your line, and then you're going to basically draw out the cross section in a different window. Okay. And then what ANSYS is going to do is that it's going to take your cross section and then orient it in a semi, okay, it's not really random, but it does it in kind of a standard way that you might not like, right? And so what can happen sometimes is that you might have to rotate the orientation of the beam in order for it to make sense. Okay. Okay. All right, but that's only something you have to worry about in method 1. Okay. All right. Any questions on this? Okay. All right. And so you know, method 2 is actually very simple to do. You know, it's just going to be you just point at a beam and then you click and then it creates one. And so, you know, all this time today, I've been talking about, you know, using shells and beams can be difficult and be kind of annoying. And so let's kind of just, I'll give you kind of a sneak preview of the activity on Wednesday to kind of show, you know, why it can be annoying sometimes. Okay. And so the main difficulty is that when you're taking parts of your model and you're reducing its dimensionality, right? And so you're basically removing dimensions from certain parts of the geometry. Basically, the main challenge is that, you know, you're going to have some geometrical inconsistencies, and so some parts that should be touching each other, that should be making connection, you know, all of a sudden they might not be touching each other anymore, right? And then what you're going to need to do is you're going to need to either extend parts or move parts around so that they actually meet up again. Okay. All right. And so just as an example, let's say that we have a thin surface, you know, like this. Okay. And then connecting to this thin surface, let's say that we have a slender surface. Okay, let's say that we have a cylindrical beam that goes like that. Okay. Right. Normally in the three-dimensional CAD, you know, these two parts here make solid contact. Right. Okay. And so ANSYS can recognize this, and so it says that, you know, these two parts of your geometry, they're connected to each other, and so it automatically will say that, you know, we can say that these two parts are bonded, or they're frictional, or they're rough, or, you know, whatever contact type that you want. Okay. But what can happen is that, you know, let's say that you recognize that, you know, this kind of black box here on the left, you know, this is a relatively thin geometry, and so let's go ahead and do a mid surface. And not even touching the slender geometry yet. And so let's say that, you know, we create a, you know, our mid surface operation just like that. Okay. And then we have this beam right here. Okay. Okay. It's a little bit hard to tell because my drawing sucks ass, but what you can basically assume here is that, you know, by creating this mid surface here that's in between these two, right? Then you're going to create a gap. Right, and so in between where that surface was and where the beam ends, right? Whereas before there wasn't a gap when there was a fully 3D model, but now that we've replaced it, you know, by a thin slender sheet, you know, now there's going to be a gap right here. And now all of a sudden, if you go into ANSYS Mechanical and then try to run a simulation on this, ANSYS is not going to recognize that as a contact, right? And it's not even going to let you, make a contact because, they might be too far apart now to do that, right? And so what you have to do in this situation is that in order to, actually run a simulation on this, is that you have to modify this geometry a little bit, okay? And so kind of the standard thing to do, and so, creating gaps is something that's very common in these ones. And so what you can do is that there's tools within ANSYS that let you extend parts of the geometry, okay? And so by extending, you can basically make sure that, when you create like a mid surface, or maybe you create or you extract a beam, right? Anytime you have, geometries that look like they should be touching, but they're not, then you can use the extend tool to kind of extend it that way, in order to make sure that it happens, right? But there's other examples too, which I can kind of draw on the next page. And so this is kind of a simple, relatively simple fix. And so this is, there's an automatic tool for this, but there are other kind of inconsistencies that can happen too. Okay, any questions on this? All right, let me draw you kind of one, probably the most annoying thing that we'll do on Wednesday, and then we'll wrap it up for today. Okay, so let's say that we have a situation where we have a beam. Okay, and so let's say that we have a very slender beam, just like this. Okay. All right, and it's making contact with the surface, that's like this. Okay. And so, I'm not going to touch the surface on this one. I'm going to focus this one on the, okay. And so let's say that we extract this beam. And so let's say that when we extract the beam, ANSYS choose to make a 1D element or 1D surface that's just like this line right here. Okay. It's a little bit hard. Maybe just draw a simple line. Okay. And so it basically made the beam, a little bit lower. Okay. And so now once again, what we have is a gap like this. Okay. Because now this beam, which should be, relatively connected to this other part, now that we've kind of reduced it to one dimension, now there's a gap in there too. Okay. But this is not a simple case to fix, because if we try to extend this beam, right, it's going to try to extend this beam this way, but what it's going to say is that, I didn't find any surface that way at all, and so the extraction is going to fail. And so what you have to do in this case is you actually have to take the beam, and we're actually going to have to physically move this up. And so we need to actually modify this geometry and kind of make up this gap right here, okay? And so we're going to move this beam upwards so that it can actually, connect together with that surface. And so situations like this where you have kind of a mismatch, this can also happen in, when you're extracting beams and stuff. And, fixing these can be, a little bit annoying, depending on how messy or how not clean your cabinet is. Okay. All right. Any questions on this before we wrap it up for today? All right, and so that's all we got time for. And so that's the introduction to shells and beams. And so on Wednesday, we're going to do an activity where we're actually going to put all of this in practice. Okay. All right. So thank you guys for coming today. Thank you everyone for tuning in. I'll see everyone on Wednesday for our next ANSYS activity. So have a good evening.
My computer. You can use it to help me with a couple.
Sure. Yeah. Mhm. probably would. I don't know if it has. It might have because it might have the classic behavior of sort of field or modern times.
Know something got here?
Yeah, probably come up.
Okay, cool. I'll be it.
Yeah.
I'm gonna do a little bit of my controls homework and I'll probably start to kind of get started on this project.
On the project?
So we never ending, bro.
So, first,
I don't do mine.
just to see what it would look like, how the elements that we could be like right now. So, and then I did this, right, work, initially, just this, right? And then I went to go create a sizing and method for this one, and I chose but then it said that the mesh would fail when I tried to mesh it on both. When I tried to generate this, and then I just tried to generate this just as one body with this already just staying the way it is, and it would then fail again. And then for this one, when I had the mesh done for this, and then I clicked generate mesh, it created a generic mesh on both of these two standard default sets.
Yeah.
And it modeled this one with texture beacons, but it actually modeled this one with texture beacons. And then when I went to go refine it, it would no longer allow me to model it with texture beacons. So is that okay that they're both in? I mean, because, well, I mean, if I just look at this, like all of my, oh, this is a lot different. Wait, yeah, this is weird.
How many different elements is this?
Oh, no, maybe this is what I'm doing. But yeah, so,
I mean, you're hardly getting any action on that side.
yeah.
You know, what elements you have there. But, you know, much more than the shape of the elements itself. So I can see that you have techniques over here.
Mhm.
But they look about the same size. And so that's going to be a much better determinant of accuracy of the simulation. Because the thing with the shape, and you know, I can't claim I 100% know how it works because, but getting a technical match on certain is really challenging. So I actually don't know exactly how. And from the methods that I know, I don't really know the generic methods. And so it's hard for me to really comment on why it's working for that one. But I also don't think it's that. As long as you're on the sides of our roughly the same, that's going to be the most important.
Yeah, and so initially the way that I wanted it, right, I did this one as 3.5 millimeters, but I thought that there was going to be a lot going on here.
Yeah.
And then this one I did it as 3 millimeters because initially I thought that there was going to be a lot more happening here than there actually is, which is why I wanted to, do a quick initial calculation.
Yeah.
And then here I did 5 millimeters because I thought there was nothing would happen. It turned out to be correct. But now there's more happening here than there is here. So we're looking at like the shear and the deformation. We have more deformation here.
Right.
Than we do over here.
Even though this is fixed there.
Yeah, fixed.
I think it's going to be because this is. I guess you're doing it.
Yeah. So where's my? Yeah, I'm doing that right there.
Yeah.
So that's as if something was smacked up.
Yeah. I mean, this is pretty far from here, and so I would say most of your action going to be probably around here. More so than here because it has to go through so many different parts.
All right now.
That makes sense.
Then I'm thinking about like if this were to be involved, then is this even really an accurate way to model the result of the force? Or
I would probably make the you can select multiple things. So you can probably get these three because having something impact on just that part might be a little bit hard. Yeah. So you can kind of distribute it. That might be a bit more accurate. So something one that's coming kind of this area right here. We can draw this one. And so I think the most important thing is you want to have it localized to a single side. Like you don't want it to spread around all the sides. You just want it to go. So, and then kind of distribute that around. So that's kind of what I would do. Maybe these two.
This. Well, that'll wrap around to the other side.
Oh, okay, yeah, maybe just.
There's the other two. Yeah, this one. Okay, all right, so I'll do this. Oh, maybe these two will work too. I don't know if they.
Yeah, you can play around.
Oh, yeah, right there. Okay, perfect. So if I do 1, 2, 3, 4. This one. Right, okay, yeah. So as if it's just getting the side of. Oh, this.
It might be fun to experiment too. So you can see what the results when you do one of those, maybe 2, 3, and then you look at it and see how that affects. It's going to affect your results.
Yeah, let's play around with it.
Yeah. I think that'd be cool.
And I definitely think it's more accurate than getting on a wider surface area.
Yeah.
I just was. I'll find out what it's doing. And then applying it on the inside, I just kind of have to select at least one at a time.
Yeah.
How do I use that? Can you just show me real quick?
Yeah. So
it's this feature.
And so you're gonna basically type, like click on the outside, so it's right here. Yeah. Left. Click hide faces. So now it's hiding exterior faces. So this one right here is the interior. And so what you need to do is click face all the exterior faces and hide all of them, and I'll just click on the interior ones. And you can right click and show all the faces.
How do I make it appear again?
Right click. So show the faces. Yeah. Okay. Perfect. It's a little bit annoying, but
Yeah, that's gonna take. All right, it is what it is. That's good. Okay.
You don't have to hide all of them. I mean, you just have to hide enough so that you can access all the interior. Okay. I think the way I did, like I did just get all the big ones.
Yeah.
I did a few of the small ones, and then from there I could twist around and click.
I'm probably just gonna press control and just start.
Yeah.
Just clicking away.
That's fine. It's just some of the smaller ones.
Yeah, definitely. I can already see how I'm getting into these things.
Yeah. So I think just do the big ones and then just enough that you can actually look inside like on the ratings.
Okay. All right, sounds good.
Yeah.
I have a quick question.
Sure.
Just in terms of, if I wanted to cut this, assembly right down the middle so I can apply that, symmetric boundary condition. I haven't
Yes.
tried it yet. I just wanted the methodology. I was thinking I was gonna make a plane there.
Yeah.
But I've never, I guess, cut in ANSYS, like, I use SolidWorks all the time, so I kind of try to make those connections.
Yeah,
But,
yeah.
I just kind of wanted the methodology, like, is that correct if I add a plane halfway down here and here?
Yeah.
Right?
Yeah, that's how I would do it.
And then how would I cut?
Yeah, I'm actually not sure. I've done it before in SolidWorks
Right.
many years ago, but I don't remember how to actually do it here. I'd have to kind of look that up.
Right, I was kind of doing some light research on how to use it, but most of it on like stuff. This is like a rod.
Yeah. I think a lot of the symmetry boundary conditions will be on geometries that are already symmetric.
Mhm.
And so to actually cut a model, I think might be a little bit.
Because I mean, you told me to apply a symmetry boundary condition. Is that different than me taking a plane down the middle and cutting that?
You'd have to do both. So you'd have to take that plane and cut it down the middle,
Right.
and then right where you cut it, then that's where you would apply a symmetry boundary.
And within ANSYS, there is a boundary condition that assumes symmetry?
Yep.
Okay.
Yeah, it's literally called symmetry boundary, but you can also do it manually. And so basically the way that you do it is you basically assume that the part can't extrude or can't protrude into that plane. So you cut
It
it
can
there.
go past.
Right,
But
because
what I'm concerned about is, okay, if I'm meshing it or whatnot, then is it gonna assume that there's a whole nother exact assembly mirror there, or is it just gonna analyze what I have cut?
it's just going to analyze what you have cut. And
Because
so
we're-
you're effectively cutting the cost in half because you're only doing half.
Right, because we're assuming whatever happens here happens here, so
Exactly.
ANSYS won't even apply any kind of conditions like
Exactly.
or
Right, and so
Okay.
your mesh is only gonna be half the size.
So you're saying do a little bit of research on how to cut it, but putting a plane there and finding out a way to get rid of the other half is kind of just the way.
Yes, yeah. And so
Okay.
I think you might, actually, okay, yeah, you're in space plane right now. And so,
Yeah.
so this is the other CAD software enhances, and we'll actually use this on Wednesday,
Mhm.
just because doing shells and beams in this one is really easy compared to that one. And so I think, because this is the one that they're actually actively developing nowadays, they're not really working on this. Like, design modeler is just kind of kept in for legacy purposes. So this is the new one that they're trying to ship.
If I'm gonna make any changes, you said call me, I'll probably work
Yes.
here. So
Yeah, I'm
not
saying-
in geometry.
Right. You'll probably find more documentation here versus in design too, just because this is the one people are using nowadays.
And I can mess with adding planes and all that within here, or am I gonna have to do that in the geometry?
You can do all that in here.
I
So
can do
this
it all in- Yeah.
this is for all intents and purposes, this is Ansys version of supplements. So this is their CAD software.
Okay,
And so you can make planes, you can do cuts and things like
okay, then I'm just gonna have to work with it. I guess I'm more just scared of geometry.
that.
I'm trying to be like, I wanna have a whole layout of everything. I wanna
Sure,
do
sure.
Before I start doing it. 'cause
Yeah.
I know what happens when you're stuck midway because you know, you didn't think something through. You don't know you're measuring and all that.
Right. No,
Um,
it's a good plan. Yeah, I should do some research on how to do some splitting, because I know other people are going to be interested in that as well.
Yeah, I
So-
will do some, and if I find something, then I'll shoot it over to you.
Great. Good. Yeah, because I was telling Jacob that, on Monday, I'm gonna do a couple of tutorials just because, one that's specific to the other geometry, which is how to hide faces. Because people are gonna want to access the interior of that pipe.
Oh, like making it transparent or just
Exactly,
for
right.
sure, just hiding it. Okay.
Okay. And another thing I think people will be interested in is how to actually insert a point. And so if you want to apply boundary condition at a specific point.
You'd have to make a sketch. Put the
Exactly.
plan on the sketch. and then
Exactly.
access it.
Yeah, and so I'm gonna do a quick tutorial on that too.
If
And then I
it
think-
think SolidWorks is usually how I can make the connection. I'm like, okay, I know how to do that in SolidWorks. Like, I've done some static analysis and all that in SolidWorks.
Actually, you should see, so if you're familiar with doing these things in SolidWorks, I wonder if you can open, because I know these parts are, they're ANSYS file format, but I wonder if you can actually open these in SolidWorks and
I
actually
can
do.
try it so they open as a SolidWorks file.
Yeah.
I think they should, because I always get stuff from customers that's in ANSYS. and I'm
Okay.
not Usually able to, because we use SolidWorks.
Okay, great. Yeah, if you can open up in SolidWorks and if you want to work on the CAD and that software, then that's by all means. Go for it.
If I can, I mean, because I know how to do what we're talking about, so for sure.
Okay.
I can make a plan.
Yeah, I'd say go for it. I mean, and that's traditionally what's done. I mean, they developed this for ANSYS just to make ANSYS a more complete package.
Right,
But honestly, most people use SolidWorks for.
right. I mean, in the job field, there's somebody that's designing this, right, and they'll hand it over to their stress analysis.
Exactly.
guy, or their dynamics, whatever it is. Yeah.
Yeah, so if you want to open this up in SolidWorks.
Yeah, it's just like I do want to know how to work in this software, so I kind
That's
of
true,
want to
that's
put
fair.
myself through it.
That's fair.
But I also have to manage my time and whatnot,
That's
so
fair.
we'll see. I'll probably try to work in it, and if it's like a bitch. I might go over, we'll see.
That sounds good.
Okay,
But yeah, I'll look into it a bit myself and see what we can do.
all right, I appreciate it. I'll
Yeah.
try it.
Mhm.
Thank you.
Yeah, sometime.
What's up?
Yeah, I have some quick questions.
Sure.
So what do you exactly mean by clean geometry?
Yeah, so by clean geometry, what I mean is, once, you'll see on Wednesday that, once we start to take, and so we're gonna do a suspension bridge, basically. And so we're gonna model a suspension bridge in ANSYS. And so once we start to extract some beams and shells, we're gonna get a lot of issues like this where the geometry just doesn't meet up with it's supposed to. And so we need to clean it up a little bit, by kind of moving some parts around and extending them to make sure they meet up. And so if you have a clean CAD geometry, ideally you don't have to do a lot of that stuff.
You do not need to do a lot of like bootcamp.
Exactly.
Okay. Yeah, because I was browsing Google, like I was trying to figure out when to use fashion conforming and fashion independent. That's something in the tetrahedron.
Yeah. So we'll go over that actually next week. So next week we're going to do I call it my lecture notes on advanced meshing, and so we'll talk more about the patch conforming. So if you want to wait until next week, then we'll definitely discuss this.
Sure. We're gonna talk about the thing that's called free phase mesh type. I think it's a setting.
So
It's a setting inside of SAD.
okay.
operations.
Okay, I don't believe I have it. I have to double check. But yeah, a lot of the stuff that I have is from directly from. There was a lot of new stuff for me too, because I didn't know a lot of those advanced features in the system. So.
I think they updated every
They don't. It's just that it's something that you don't really learn until you're forced to use it. And so this class is unique because I'm going way more into Ansys this class than I've ever done in previous classes. And so I really wanted to go into like what are all the advanced features that I could find. And so I did a lot more research for this class than I have for.
So yeah, one of the things that I've been looking into in the project. So
Yeah.
So two of the things that I think I've encountered difficulties would be like, I'm wondering what kind of solution should I be getting? Like, there are a lot. I mean, in the previous Ansys activity, we need to do stress and the three directional normal stress, but I'm not sure whether the three directional normal stress.
Hold on, man, I'm just suppressing the shit I want.
Or because I would also like to
I'm just suppressing the shit. I'm pretty much gonna suppress this whole thing and do the analysis on the house.
yeah, like that. So I'm trying to figure out which solution.
Yeah, I would start with total deformation. I would start with equivalent stress, and I would start with equivalent strain. I would start with those three. I think that's just kind of your favorite there. And then if you have some reason to go back to normal stress or shear stress, then you can start looking into those two. I would start with those three, just to check the results. Because I think what you're going to run into is that you're going to run a simulation, and then you're going to need to check if that if the simulation actually looks right, or does it actually look feasible. I'd say those three are the bare minimum. Say, okay, deformation looks right. The equivalent stress looks about that looks about the right stress, and the strain looks about right. Then you can start looking at what is the shear stress.
All right. So I think what kind of solutions we're going to use depends on the objective.
Exactly. Yes.
All right. So I was also wondering, I'm also kind of working on the growth law.
Yeah. Okay.
So from my understanding, it's kind of like the water, the growth fluid.
Yeah.
So I was wondering, if that's the case, isn't the force, I mean the load applied on the structure would be like free, like from all sides of the interior, like because the fluid will be applying forces on all.
Yeah, you're gonna have basically hydrostatic pressure on the inside of the.
So that's the only one loading scenario that I can think of.
That's one of them. Yeah, so you can also think of what are some exterior things too. So I think you're thinking of what's the general use application of that. And so what's a typical everyday for that whole valve. I think just having fluid running through it, that's pretty typical. But you can also think of what are some emergency situations that can happen too. Think of along those lines. And so be creative with it. Think about where, and so think about where does a political valve like this use, like what kind of facility, and what kinds of things can happen in the facility, or to create some undesirable load situations. Yeah, because the good thing about simulation is that whatever you simulate doesn't happen in real life, and so you can simulate all kinds of crazy simulations.
Yeah. So one of the things that I've been looking into.
Okay.
So I've gone through like the first chapter. So
Great.
my plan right now is to go through the whole textbook and
Okay.
by the end of January.
Okay. Okay.
So
Yeah, so that I think that's a good time because then, because I still need to order the computer. Yeah. And I still need to order the lenses, and I think it's probably not going to come in until around that time too. So once we do that, then I think then the computer will be ready for you, and software will be ready for you. And in the meantime too, I can send you the files that Jonathan worked on. I think you can try and see what you can do with this right now with those files based on what you worked on. And then whatever. I'm guessing what's gonna happen is that you're not
The
gonna have enough
system
power
is Hurwitz, so
within
does that
the,
mean it's stable?
within
The
the
system,
security
if you
software.
prove that the
Or
system.
even,
is
or even,
Hurwitz,
you can use, these are gonna be
Who
much
would
better.
say
than
that?
super transport. It's just-
But
That's
it
a
says
question.
for the-
When it-
but
when
it says
you
for
use more
the
power,
CTI, the CTLTS system,
Mhm.
it has to be
So, yeah, so, yeah, keep on working through that.
exponentially stable.
Let me get in contact with
All
John.
eigenvalues have to be in the
Those
profile.
files, and then I'll get those to you.
Mhm.
So I'll let you kind of.
Yeah,
Yeah,
It'd be really interesting to
but
compare.
Hurwitz just
Try-
tells you
try
that
to
it's
recreate
asymptotic.
Jonathan's conditions and so
right, and then
we should
you
compare
have
what you
different
get.
criteria to determine if it's stable, right? Because when you do reserve, you don't know the
Compare
whole,
to
you don't know,
the actual experiment.
you don't have,
So I think we
any
can
of
have
those
like a
values, you
three-pronged
say, hey,
here.
if all my leading coefficients are positive, and they're not switching
Yeah,
signs,
no, they're not.
then,
I found that.
I
I
might say,
yeah,
well, you don't know that. You don't have to solve it.
So,
That's what's different
But I-
about reserve, right? You're not getting the roots at, you just have to follow them.
yeah.
Yeah. What
Oh,
I'm saying is
yeah.
that Hurwitz tells you
Yeah.
whether or not your eigenvalues
That's
are negative.
Well, yeah.
I
okay, so-
don't
but
actually, so I
If you
only
want to
have.
go on and figure them
I
out,
only
yes,
have.
you know that they're
No, that would do, I think.
if your root curve is
Okay.
Yeah, I would-
So that means that now we know that it's asymptotically stable.
Oh,
And
do
we
they
know
have
that
work?
the-
Like, do
And
they
we
have,
know that the eigenvalues are
Like,
negative.
do they have the example?
Like, what about, how do we know if it's exponentially stable?
Yeah, they
Okay.
have like, wait,
I don't think the root curve
Yeah.
can tell you that.
I mean, the content are mostly like two colors.
Okay, okay.
I don't think you
Yeah, I would
can
just
get
focus on this.
asymptotically or exponentially stable from the root curve. You just know it's stable. You don't know.
Do you do some of the exercises? Of course, it's hard.
So, I think it tells you if it's asymptotically stable.
But yeah, just, I would say it's very.
Asymptotic stability of the equilibrium state.
Just get a
X
good
equals
feel
zero.
for
This can be concluded immediately based on the Hurwitz criterion.
Okay,
So if
then
it meets
yeah.
that criterion,
Okay.
then it's asymptotically stable.
Can I ask you
Professor?
one more short question?
Sure.
Go, go
Do you know about this?
for it.
So it says that a system is stable if it, I'm sorry, I know I asked.
You're gonna hit it
I
with
said
that
you
right
have to
now?
brush over it. So the roof Hurwitz tells you it's asymptotically stable, but does it, so how does this go? Like, okay, so this is asymptotically stable and then these are two lesser criteria. So if it's asymptotically stable, does that automatically tell you it meets these two lower criteria for stability?
LTI is exponentially. I've never heard of exponentially stable before.
Okay,
Don't even mess with it.
it's okay. You don't have to, like, think about it.
That's
I
like
was
deep
just-
into.
Like, I was
controls,
just
like-
curious, like, if you knew about it right off the top of your head.
I
Could you, like,
don't.
Help me?
Oh, no,
Yeah,
no.
okay. Sorry,
Yeah,
I know.
I
you're-
know-
you're-
I know
you're a
asymptotically-
fluids guy, yeah.
Asymptotically stable means that if we draw kind of a line or an asymptote, then it'll approach that line.
Right,
and become stable.
The stability.
Yeah, exponentially stable, I don't even know, because usually when something's exponential, it just grows exponentially like that. Unless the exponent is negative, then it goes down.
Right, which is what we're looking at when we're talking about negative.
I see, I
That's why you know it flows like if you don't have negative.
Yeah, maybe exponentially stable means that it approaches the asymptote with an exponential dependence. Because you can also approach the asymptote with polynomial dependence, but exponential is like really tough. So that's what I'm guessing it would be, but I've never quite heard that term before.
So it would basically approach the asymptote extremely quickly as if it was
Exactly.
exponential and level up right before it hits the
Right.
asymptote. Okay.
Right, so if you actually solve for like an analytical expression for the whatever function it is, there should be an exponential term.
Okay.
I have one quick question
Sure.
that has nothing to do with controls.
Uh-huh.
So, I want to possibly get away by suppressing this bearing.
Yeah.
But how would I, how am I trying to ask this question? How would I set this up in ANSYS where, because this is just floating right now.
Yeah, so it would be hard because right now you can't really establish a contact
Correct.
between the shaft and the housing because they're a little bit too far apart. You can try to force it, and so you can try to create like a manual contact and then say that, I want to make a bonded contact between this surface and that one. I don't know if it will allow it though, because they're not actually touching.
Right.
And so on Wednesday, we're actually going to create some manual contacts because the shells and beams kind of screw up the geometry quite a bit. And so you can try to create a manual one. I don't know if it's going to work though, but you can try it. and
The
see.
problem is like, I care about the housing, right? How the housing is going to pretty much withstand the load, right? I'm trying to do a yielding scenario.
Right.
How much load can I handle before? And I don't know how I would mesh this if all this is in the way when I don't really care about what this bearing is doing.
Right.
I
Yeah.
care about what this bearing and this shaft and the load is acting upon the house.
Yeah. Sometimes you kind of have to bite the bullet sometimes and mesh things that you don't really care about just because it's
I can just mix match that and just
exactly
put massive elements and
Right.
not really give a shit about it.
Right.
And then refine. Now, see, now I'm talking, now I need to know how to like hide this and then refine my mesh in there.
Right.
Because that's what I'm concerned about, and then just have this kind of be normal.
yeah. Sometimes you have to do that just because like a lot of times it's because of boundary conditions too. Sometimes you just have to include things in your model that you don't really care about, but it's just so convenient to put a boundary condition there. So it happens sometimes, and so I think this might be one of those cases.
Okay, I'm gonna try to get something together so I can at least show you.
Okay.
Instead of staring at it.
Okay. Yeah, sounds good.
All right, thank you.
Yeah, I got it. It's 7:15.
Well, speaking of suppressing
Yeah.
the things, like in the midterm we suppress the nuts and bolts, but like I'm just curious, like in like industrial simulation, they're not gonna suppress it, right? Because the nuts and bolts are like